Welcome, Math 1111ers, to Lecture 3.1. Before we get going with this material, I just wanted to let you know that I don't cover all parts of 3.1, just the parts necessary for you to understand logarithms so that you can work logarithmic and exponential equations later on in the chapter. This is our last chapter that we're going through together, so I hope that these videos have been helpful for you. If you have any suggestions, by all means, send me an email and let me know what you have to say. I'd love to hear from you. Without further ado, we'll get going with Lecture 3.1. Okay, so the first thing that I'd like to talk about in 3.1 is the natural base E. Now, E is a symbol that stands for an actual value, and this value is the idea of a limit. So it is a number that is approached as in or part of the formula that makes up E, the value. As that number goes higher and higher, the value E is approached. It's sort of not really, because pi is not really a limit, but it's sort of like pi in that we have a symbol, but it's a value that we're talking about. And we have a particular value that we round to when we are using E for calculations without a scientific calculator where we don't have the value E to plug in. We'll go ahead and get going with this. Let me grab my pen. I'm going to use a little bit thicker pen today. All right, so E is defined as the formula 1 plus 1 over n to the nth power. And this is as n approaches infinity. So we're going to use this chart below to see what happens to this value as n gets bigger and bigger. We'll think about it for just a moment. N lives in two different places. So as this n right here, which they're the same n's, but as n gets bigger, that particular fraction that you're adding to 1 gets smaller and smaller and smaller. However, you're getting bigger and bigger and bigger with the amount of times that you multiply it by itself. So it'll be interesting to see what happens. We're going to go ahead and move through this chart to begin to discover what value E approaches. So with this first one, we have 1 plus 1 over 1 to the first power. Oops, that's an equal sign, which is 2 to the first power, or just 2. And I'm going to have to go back to my smaller pen to write in this little chart here. Okay, when n is 2, we have 1 plus 1 over 2, so that's really 1 plus 1/2 squared, or 1.5 squared. And when I put 1.5 times 1.5 into my calculator, and let me just let you know, I normally have my graphing calculator. I've just got a scientific calculator today, so it may take me a moment. Usually I just kind of insert a new value, and I don't have to type this over and over again, but I'm going to have to type it over and over again today. Okay, so when n is 5, we have 1 plus 1/5 to the 5th power. So 1 and 1/5, 1 plus 1/5 is 1.2, and when I raise that to the 5th power, I get 2.48832. Okay, I'm going to start running out of room in these blocks to write the actual formula here, so this is the last one that I'll actually write in, but it's always gotten by just plugging in your new n value. Because this is 1 plus 1/5 10th raised to the 10th power. So that's 1.1 raised to the 10th power. And we get 2.59374246. And yes, I'm going to write all those values out as much as I can. Okay, so when n is 100, I have 1.01 raised to the 100th power. So once again, that fraction's getting smaller and smaller, but you're raising it to a bigger and bigger number. So we are going more positive. 2.70413829, and then 1 plus 1 over 1,000 raised to the 1,000th power. 1.001 raised to the 1,000th power is 2.716923932. Okay, 1.0001 raised to the 10,000th power is 2.718145927. And it gets more and more important to take that out to more and more decimal places so you can see the difference in them. Okay, 100,000. So let's see, tenths, hundredths, thousandths, 10,000, hundredths. And that value is raised to the 100,000th power. And I get 2.712682237. Woo! Okay, 1 in 1 millionth. So 1.10 hundredths, thousandths, 10,000ths, 100,000ths, 1 millionth raised to the 1 millionth power. I get 2.718280469. And finally, we'll try to the 1 billionth power. Okay, so 10ths, hundredths, thousandths, 10,000ths, 100,000ths. Let me do this a different way. 1 divided by 1 billion. 1, 2, 3, 4, 5, 6, 7, 8, 9 zeros. And raise that to the 1, 2, 3, 4, 5, 6, 7, 8, 9, 1 billionth power. And we get 2.718281827. Okay, so hopefully you can see that because that fraction's getting smaller and smaller to such minute quantities, that this is really only going up in the 100,000th power. We estimate E to be approximately, let me get a different color here for the unveiling of E, and I'll get a thicker pen as well. We approximate E to be 2.71828. A lot of times we have an E button on our scientific calculators, and whenever you hit E, you're always going to get something to raise it to. So you've got to raise it to a power, whether it's the first power or the second power or whatever. If you don't have a scientific calculator, which everybody should have a graphing calculator, but if you were in a case where you didn't have a scientific calculator and you needed to estimate something using the value E, most people would just use 2.718. All right. So, sorry about the dogs crying in the background. They are ready for their lunch and ready to go out into the fence and run around. All right, let's move forward. Okay, so the reputation the gray wolf acquired in the U.S. in the 19th century Okay, sorry, I took a quick little break there to feed the dogs. You can probably hear them crunching in the background now. All right, so the reputation of the gray wolf acquired in the U.S. in the 19th century and early 20th centuries was one of insatiable killer. Although the label was undeserved, an estimated 2 million wolves were shot, trapped, or poisoned. By 1960, the population was reduced to 800 wolves. The figure shows the rebounding population in 2 recovery areas. Let me show you. So here are the recovery areas. After the gray wolf was declared an endangered species. The exponential function. Okay, so the reason this particular function, and I'll write it over here, f of x is equal to 1.26 e to the 0.247x. The reason this is considered an exponential function is because your variable for the function is living in the exponent. So this is considered an exponential function. This models the gray wolf population of the northern Rocky Mountains, f of x. So population x years after 1978. So that x is standing for years after 1978. The wolf is not removed from the endangered species list, and trends shown in the figure continue. Project its population in the recovery area in 2010. So, we're going to use this formula, and basically we need to figure out how to get the value 2010 up into the exponent. But remember, the exponent, the variable in the exponent is standing for years after 1978. So we've got to figure out what that is before we can plug it in. So 2010 minus 1978 is 2010 minus 1978 is 32. So we are going to plug in an x value of 32. So this is what it looks like, what I'm about to do in my calculator. I'm about to do f of 32, which looks like 1.26 times e raised to the 0.247 times, and here's where we're going to plug our variable in, 32. All right, so I'm just going to put this into my calculator, and when I multiply 0.247 times 32, I get 7.904. So this is 1.26 times e raised to the 7.904. All right, and then I just put that into my calculator. 1.26 times e, I'm looking on this particular, okay, there is e to the x. Let's see, so shift e to the 7.904. Let's see what we get. Oh, it's giving me a syntax error because I don't have my good calculator. Let me figure out how to use this one. Okay, so e to the e to the 7.904. Okay, I'm going to pause and figure this out real quick so you're not having to listen to me figure it out on this calculator. Okay, I'm back and I've got my calculator figured out and the dogs are outside and happy. So here we go. All right, so to do this calculation, I need to raise e to the 7.904, and then I'm going to multiply that value by 1.26, and I get approximately, wait a minute, this isn't right. Sorry, I'll pause again. Oh no, this is right. I'm not going to pause. Okay, so I get approximately 3,412. So approximately 3,412. Hopefully that calculation's right. Y'all check it on your graphing calculators. And like I said, I'm kind of handicapped with this little scientific calculator because they all work so differently. So I'll go ahead and move forward. I forgot to tell you what that was. That's how many wolves are in the population in 2010 in the northern region. All right, now we'll move forward. Okay, so this whole idea leads to compound interest. Now, before we start looking at compounding interest, we need to take a look at how this formula is built. So, A is the accumulated value on the account, and so with simple interest, if I take my principal, P, and add that to the rate I am given on an account, let's say this is a savings account at 10%. Now, you're never going to have a savings account at 10%, and those aren't simple interest problems, but let me give a better example. Okay, so say I purchase a pair of jeans that cost $10, and there was 10% sales tax. I would take the purchase price or the principal, $10, and add it to the rate multiplied by that principal. So that would be one more dollar because 10% of $10 is $1. That would give me my account total or my accumulated value of $11. So that's how you find out a total value when there is interest charged on something. So if I were to factor that formula, I could pull a P out of both of these terms, and I'm left with 1 plus R. Okay. So this is important to understand to see how this formula builds itself here. All right, so we're going to do accumulated value for each compounding, and compounding is just how many times that interest gets calculated and placed back onto the account. And let's say we have that savings account with $100. It compounds monthly 10% a month. Well, at the end of the first month, you're going to have $110 because it adds that 10% on. However, at the end of the second month, let me write this down. So the first month, say you start out with a principal of $100, you're going to add the 10%, so that's 100 times 0.10, onto that account to get $110. Well, the second month, you don't go back to starting with $100 and take 10% of that. You start your next month with your new balance, $110. You're going to add 10% of that onto there, which would be 110 plus 11, which would give you 121. 121 would be your new account balance starting the next month. That's what compounding interest is. It gives you interest on the new balance, you know, however many times it's compounded. The time is always given in years. So let's see what happens as we move through higher and higher T's here. All right, at 0 years, we have just our principal. We haven't accumulated any interest. After 1 year, we have our principal plus the interest we gained on that amount, which is our principal times our rate. And as I told you before, that can be factored as P times 1 plus R, if you factor that P out front. All right, so this new, I'm going to highlight this in a different color. This is our new account balance. So at the beginning of the next cycle, that is our new principal balance. So when we start with our principal, our new principal is now P times 1 plus R. It's what we were left with at the end of the last cycle. And we have to add on, so I'm going to use the blue again. We have to add on our rate of our new principal. So there's our new principal and its times that rate. Okay, so now I have, let me get a different color. Now I have a common factor that I can factor out front of P times 1 plus R. So if I factor that out, I promise this will be clear as mud in just a moment. If I factor that out front, I have P times, oops, let me go back to my green, that is my common factor. So P times 1 plus R is my common factor now. And what I'm left over with, I'll go back to my blue. So when I factor it out of that first term, I'm just left with 1. And when I factor it out of that second term, I'm left with plus r. So I factored it out of this first term right here and was just left with the 1 here. Let me get a different color. Get a yellow. So I factor the p plus 1r out, and I'm left with 1 in that first term. And then I factor the p plus 1r out, and I'm left with r in the second term. So if I simplify that particular expression here, I could call this p times 1 plus r squared, because I have 1 plus r times 1 plus r. That is my new principal. So here we go. I'll write my new principal in pink again. So p times 1 plus r squared is my new principal. And then I have to add on the interest. So that is my principal, p times 1 plus r squared, times my rate, r. Okay, so here's the factoring again. I now have a common factor of p times 1 plus r squared. It shows up here, and it shows up here in both of the terms. So I can factor that out front, p times 1 plus r squared, and I'm left over, when I factor that out, with 1 plus r. So I can call this p times 1 plus r cubed. So now I have 3 1 plus r's. And let me point one other thing out so that we can go ahead and build this formula. Notice when I have 1 year of compounding, I have p times 1 plus r to the first power. When I have 2 years of compounding, I have p plus 1 plus r, p times 1 plus r squared. When I have 3 years of compounding, p times 1 plus r cubed. So without even having to do all of this factoring business, I know that when I have 4 years of compounding, the formula for that is p times 1 plus r to the 4th power. So I can generalize this to say p times 1 plus r to the t power, meaning however long that thing is compounded in years is what that expression is going to be raised to in the exponent. So most savings institutions have plans in which interest is paid more than once a year. Like with savings accounts, it's usually either monthly or quarterly, just depending on your own savings account. So if interest is compounded twice a year, then we have a compounding period of 6 months. That's semi-annually, so twice a year. When compounding interest is paid 4 times a year, we say that's compounded quarterly. Some plans allow for monthly, so that would be compounding that interest 12 times a year. We also have daily. Now, intuitively speaking, if you compound daily, you would think you use 365 because there are 365 days in the year. However, for finance purposes, and I'll write this here, when you compound daily, you have 360 times per year. So in general, when interest is paid, let me get a different color. When interest is paid n times per year, so however many times per year, we say that there are n compounding periods. So let me point something out. When you're using this formula, it doesn't take into consideration that it may be compounded more than once a year. So we have to modify that particular formula to account for how many times a year is this thing getting compounded. And so say you have a rate with your bank of, we'll make it easy, and do 12% a year compounded monthly. They don't give you 12% of your account every year. I'm sorry, every month. What they do is they take that 12% and they divide it up over how many times they're going to compound it that year, which if it's monthly, it would be 12. So actually you'd get 1% per month, and that's going to be compounded 12 times that year. So the formula for compounding is given as A is your account balance, is principal times 1 plus, we don't say R, we take our rate, that's an R, and divide it by however many times we compound it. So if we had that 12% rate compounded 12 times a year, that'd be 0.12 divided by 12. And then we raise that not just to however many years, but however many years times however many times it compounds per year. So our compounding interest formula is P times 1 plus R over N raised to the NT. So let's take a look at an example using this formula. And I'll write the formula up here as well. We have account balance equals P times 1 plus R over N to the NT. Okay, so you have $6,000 to invest, and basically we're going to compare two investments and see which one's a better deal for us. So I'll do this first one in purple. So we have $6,000 to invest in one of these investments. We have one that both of these investments are going to be over 4 years. We have one that is at 8.25%, and it's compounded quarterly. And then, let me get a different color. I'll do the other one in green. So the other one, we still have the same $6,000. It's still going to be over 4 years, but it's going to be 8.3% compounded semi-annually, so twice a year. All right, let's do our comparison and see which is a better deal for us to invest in. Whenever you use a formula, you should always write it down. So the formula that we're going to use for both of these is A equals P times 1 plus R over N raised to the NT. A equals P times 1 plus R over N raised to the NT. Okay, so I'll start out with the first one. And my P is $6,000. That's my principal, or the money that I start out with to invest. My T is 4 because T is always given in years, and I'm told I want to invest this for 4 years. My rate is 8.25%, but I don't want to write it as a percent. I'll write it as a decimal, so 0.0825. And it's compounded quarterly, so 4 times a year, so my N is 4. All right, now all I have to do is plug my values in there. So I get A equals 1 plus. All right, I'll go back and fill in the values with what I've been given. Okay, so my rate was 0.0825, and that's going to be split 4 ways. And then I'm going to be compounding for 4 times a year for 4 years. So raised to the 16th power. I'll just simplify this a little bit. A equals 6,000 times 1 plus, let's see, point. If I had my graphing calculator, I'd just be doing it all in one chunk. 0.825 divided by 4 is 0.020625 raised to the 16th power. I'm going to go ahead and add the 1 onto that, so 1.0, and I'm going to raise that to the 16th power, and then I'm going to multiply that by 6,000. And I get, at the end of 4 years, if I didn't add anything else into the account, my account balance would be at $8,317.84. Okay, now let's check the other account. So I still have a principal value of $6,000, and my time is going to be for 4 years. The rate with this one is 8.3%, so 0.083, and my compounding times is twice a year. So I have a higher rate, but I don't compound as much with this one. All right, I'm going to go ahead and fill in my formula here. So my account balance will equal 1 plus. All right, I'm going to come back and put my values in. So I have 6,000, 0.083 over 2 raised to the 2 times 4. Okay, so I'm just going to simplify this a little bit before I put it in my calculator. Okay, so 0.083 divided by 2 is 0.0415, and that's all raised to the 8th power. So I'm going to add 1 and raise that to the 8th power, and then multiply that by 6,000. And for this one, I get an account balance of $8,306.64. So although it's a pretty minute difference in the account balance, so we have this account balance here and this one here, very minute difference. Over a longer span of time, that first account, since it's compounded more often, even though it's got a lower interest rate on it, is going to build quicker than the account with a higher interest rate but not compounding as many times per year. So this is an important lesson when you go to invest, that you really want to look at how everything is going to affect that account balance, because off the top, most people would have chosen the higher interest rate, when in actuality, that lower interest rate, but compounding more times a year, is more beneficial to you. So I hope that this was an interesting problem for you to see. All right, so let's move forward. There we go. All right, now we need to talk about another concept, and that is compounding continuously. So I'm not even talking about compounding daily. I'm not even talking about compounding every second. I'm talking about continuous. It's nonstop. It's infinite. It keeps going and going and going. These are how your credit cards are compounded. Okay, so I'm writing that in red. Credit cards, very bad. All right, so if you've ever tried to pay off a credit card, you may have noticed that if you just look at your account balance online or you receive a bill in the mail and then you send that money in, you'll probably receive a bill the next month for like, I don't know, 28 cents or something crazy like that, because your credit cards are continuously compounding. Like the balance on your credit card right now is different than the balance on your credit card right now. So if you want to pay a credit card off, what you have to do is call the credit card company and give them an estimated date as to when your payment is going to arrive, and they will calculate it out to that date and give you a future balance on that. Okay, so let's go back in our lesson and look at the compounding interest formula. Or we'll just go right. We'll go right here and look at the top on the last page. If you notice, the inside of your, the parentheses here is 1 plus r over n raised to the nt power. Well, if we go back and look at the value e, it should look very similar to the parenthesis portion of your compound interest formula. And don't forget that we approach this value here, e, as n approaches infinity. Well, n in your compounding interest formula is standing for how many times it's compounded per year. Well, if we flash forward to continuously compounding, that n is moving to infinity. So, if we start out with a equals p times 1 plus r over n raised to the nt power, and now, since we're going to continuously compound, that n is moving towards infinity, our new formula for continuously compounded interest is a equals p times e raised to the rt. We call this the Pert formula. So continuously compounding, you use the Pert formula, not the compounded interest formula. So this is just regular, this is finite compound interest. This is continuous or infinitely compounding interest here, the Pert formula. So we'll take this situation below to see what happens. You've taken out a credit card that has a $1,500 limit. Let's say you went bonkers and maxed it out the first month you had it. Which that did happen to me when I first started college. They used to give out credit card applications like candy, and they would give anybody credit during those days. So I did this very thing. I had a credit card. As soon as I started college, they gave it to me. They used to let the credit card companies set up tables on campus. And they'd like give out free t-shirts if you signed up for a credit card. So I was like, sure, I get a credit card and a t-shirt. Anyway, I maxed it out the first month. And, you know, if you miss a payment with a credit card, you may get to have this really low introductory APR, which is your annual percentage rate. But if you default on that and miss a payment, it's going to skyrocket. So that's what happened to me. You know, I missed your first payment. By the way, I'm much better with money now. And as a matter of fact, we don't use credit cards. We don't deal in credit at all. The only credit we have that is out there is our home mortgage and our student loans. Now, we do have a credit card that we use online, but we pay it off monthly. So I'm much better with credit now because I don't ever carry a balance. All right, so you miss your first credit card, or you miss your first payment, and it skyrocketed to 29% interest. It is also time to purchase your textbooks and pay your tuition. So you're not able to make your monthly payment now, not even your minimum payment on your credit card balance. So this is a terrible, terrible idea, by the way. So you're going to let your credit card balance just sit, and it's accumulating all that interest. So we're not even going to consider the fees that they're going to be charging you out the wazoo. And by the way, they're going to turn this credit card off, but it's still going to be accumulating interest. So if you allow your debt to sit for 2 years until you graduate from GHC and you make no payments on it, what will your account balance be at the end of those 2 years, given that your debt on this credit card is continuously compounded? So we're going to use the Pert formula to figure this out. A equals P times E raised to the RT. My P is my principal balance, so that's that $1,500 that I charged up as soon as I got that credit card. E is a given value. We've already discussed that. My rate is a whopping 29% now that I missed that first payment. And the time is always given in years, so I'm going to let that accumulate for 2 years. So let's see what happens to this $1,500 at the end of 2 years compounding continuously. A equals my principal balance, $1,500, times E raised to the 0.29 times 2. Okay, so 0.29 times 2 is 0.58. So I'm just going to simplify this so I can put it in my little scientific calculator here. E raised to the 0.58%. Okay, so E raised to the 0.58, and then I'm going to multiply that by 1,500. So very low balance. Whoa! At the end of 2 years, I will owe, and once again, this is not including all the fees they're going to slap on you for missing credit card payments. This is just on the principal. $2,679.06. Moral of the story is, don't get a credit card unless you're prepared to pay the balance off monthly. It's a good idea to establish credit, especially if you're going to want to use credit to buy a car or something, which I have learned in my older age that the best thing to do is just save up the money and buy a used car. That's how I've bought my past 2 vehicles, and it's the most wonderful feeling not having a car payment. But if you need to, you may need credit at some time in your life to purchase a house or something like that. So you can go ahead and get that credit card, but make sure you're paying off that balance monthly. So that's what my husband and I do. We use our credit card to purchase online because that protects us when we purchase online, and then we pay that balance off as soon as the credit card bill comes in at the end of the month, and do not carry a balance over to the next month so that it does not accrue any interest, because you have a 30-day grace period with most credit cards. So that is my not only example to help you understand continuously compounding interest, but also my dire warning against credit cards. All right. And then the most depressing part of the lesson, and that is talking about the United States national debt. Now, if I'm in a face-to-face class with you and we're talking about this, we talk a while about the difference in the national debt and the deficit. So these are two different things, and you'll actually hear people on the news using debt to mean deficit. And I challenge you, go look up those words, because it will be shocking when you find out what the deficit is as opposed to what the national debt is. Okay, so before I started this lesson earlier, I went to the United States debt clock to see what the national debt was at. And I rounded it to the nearest billionth. And here's what we have. Right now, the United States is sitting at about 17 trillion $568 billion in debt. So by the way, when you hear, oh, we've lowered our deficit to $1 trillion a year, that's not the debt. That's just how much debt we're accumulating that year. The deficit is the discrepancy between our exports and our imports. So basically, we are spending $1 trillion more than we're making every year. That's our deficit. So that our deficit accumulates into our overall debt. So this is our debt that we're sitting at right now. Well, this is where we were sitting about an hour ago, rounded to the nearest billion. So this problem that I'm presenting you with is very contrived. It's just kind of an eye-opener type thing, one more way to practice with the Pert formula. So I've just made up like the percent, our interest rate and stuff like that, because really I have no idea what we're charged in interest on our debt. So if we borrowed no more money this second and our interest rate is at 2%, 1 year from today, how much would we owe? And hint, we're continuously compounded. So we're going to be using the Pert formula. Our account balance is PE to the RT. All right, so once again, we're talking trillions here. So our account balance is equal to our principal, 17,568 billion times E raised to the R. Our rate is 2%, and we're going to do that for 1 year. All right, so I'm going to put this into my calculator. I'll raise E to the 2%. And I'm going to multiply that by 17,568 billion. So 1, 2, 3, 4, 5, 6, 7, 8, 9 zeros. And I get, okay, I'm going to have to write this number down and count up my decimal places because my calculator won't show this many numbers. 1, 7, 9, 2, 2, 8, 9, 7, 1, 4. Okay, so that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. I think that should be, yeah, correct. All right, so that would be our new account balance after 1 year. And if you want to see how much of that was just in interest, I would subtract off what we started with, 6, 8, 0, 0, 0, 0, 0, 0, 0, 0, 0. And just in interest, so let me subtract off what we started with, 17, 5, 68, 1, 2, 3, 4, 5, 6, 7, 8, 9 zeros to give us interest to the tune of 3, 5, 4, 8, 9, 7, 1, 4, 1, 6, 0, 0. So just in interest, if we borrowed no more, which we're borrowing continuously, but if we borrowed no more, over 1 year, our interest on just that amount would be $354 billion $897,141,600. Ouch. All right, I hope that this lesson has helped you to understand compounding interest in the natural base E a little bit better. Don't forget that Unit 6 stuff is coming up. This is our last unit, yay! And it will be due Monday, April the 28th, which is the first day that final exams begin. Uh-oh, that's the last information. The quiz is going to open, let me check my calendar here. If it ends on the 28th, that means it opens on the 24th. Sorry about that. I forgot to change that from the last slide. The 24th. And tomorrow's lecture will start at 3 o'clock, and it's going to be over section 3.2. Don't forget, registration for fall for everyone opened today. So go register for fall classes if you haven't already. Have a great day.